If you're a tech enthusiast, then you need to know how superconducting qubits are changing everything. Ready to unravel the future? Superconducting qubits. Sounds fancy, right? But what are they? Imagine them as tiny wizards that can store and process information way faster than your regular computer bits. Now here's the game-changer. Physicists at the Institute of Science and Technology Austria have made a breakthrough. They created a fully optical readout for these qubits. Why does that matter? Because optical signals can travel faster and cover longer distances without losing information. Think of it like upgrading from a horse-drawn carriage to a high-speed train. This development could lead to super-efficient quantum networks. Imagine a quantum internet. The future looks bright, and it's all thanks to these superconducting qubits and their optical readouts. We're talking faster computations, more secure communications, and a tech revolution on the horizon. So, next time someone mentions quantum computing, you can tell them it's not just sci-fi. It's happening now. Stay tuned for the next part where we dive deeper into the fascinating world of superconducting qubits and their applications. Don't forget to like, share, and subscribe for more tech magic. Catch you in the next Quantum Leap. I bet you didn't know that quantum computing could revolutionize our world. Imagine a computer so powerful that it could solve problems in seconds. Problems that would take classical computers billions of years. This is the promise of quantum computing. At the heart of this revolutionary technology lies the qubit. Unlike classical bits, which can only be 0 or 1, qubits leverage the strangeness of quantum mechanics. They can exist in a superposition, being both 0 and 1 simultaneously. This unlocks unprecedented computational power. But building a quantum computer is no easy feat. Qubits are extremely fragile and susceptible to environmental noise. Maintaining their delicate quantum states is crucial for performing complex calculations. This is where superconducting qubits come in. They offer remarkable stability and are therefore a leading contender in the race to build large-scale quantum computers. Superconducting qubits operate at extremely low temperatures, just a hair above absolute zero. This minimizes thermal noise and allows them to maintain their quantum states for longer periods. However, reading the state of these qubits currently relies on electrical signals. These signals introduce their own set of challenges. This is a bottleneck that researchers have been working hard to overcome. Superconducting qubits are incredibly promising for quantum computing for several reasons. First, they are relatively large compared to other qubit types, making them easier to manufacture and manipulate. Second, their superconducting properties allow them to maintain their quantum states for a remarkably long time. This is crucial for performing complex computations. However, there's a catch. Reading the state of a superconducting qubit requires sending electrical signals to the cryogenic environment where the qubits are kept. This process has several drawbacks. First, electrical signals generate heat, which can disrupt the delicate quantum states of the qubits. Second, managing numerous electrical connections at extremely low temperatures is technically challenging and expensive. This reliance on electrical signals has been a major obstacle to scaling up quantum computers. The more qubits you have, the more complex and heat-generating the wiring system becomes. This limits the number of qubits that can be practically integrated into a single system. Clearly, a new approach is needed to unlock the full potential of superconducting qubits. Enter a team of physicists from the Institute of Science and Technology, Austria, ISTA. They have achieved a groundbreaking feat: fully optical readout of superconducting qubits. This means they can determine the state of a qubit using light instead of electrical signals. This breakthrough has the potential to revolutionize the field of quantum computing. The ISTA team's approach is ingenious in its simplicity. They use a special type of superconducting qubit that is sensitive to light. By shining a microwave pulse onto the qubit, they can change its resonant frequency depending on its quantum state. This frequency shift can then be detected optically, revealing the qubit's state without ever sending an electrical signal to the cryogenic environment. This method eliminates the heat generated by electrical signals, paving the way for more densely packed qubits. It also simplifies the design and reduces the cost of quantum hardware. This breakthrough is a significant step towards building larger, more powerful quantum computers. The use of light for qubit readout opens up exciting possibilities for quantum communication. Fiber optic cables, already the backbone of our internet, can transmit vast amounts of information encoded in light. This same technology can be harnessed to connect and communicate with qubits. Imagine a future where quantum computers are interconnected via fiber optic cables. This would allow for the creation of powerful quantum networks, capable of solving problems that are impossible for even the most advanced classical computers to tackle. Moreover, fiber optic communication is inherently resistant to noise and interference, ensuring the fidelity of quantum information transmission. this is not just a pipe dream. Researchers are actively developing technologies to make this vision a reality. By leveraging the power of fiber optics, we can unlock the full potential of quantum computing and usher in a new era of technological advancement. Section 5. Bridging the gap from light to microwave and back. While using light for communication is promising, there's a hurdle to overcome. Superconducting qubits operate in the microwave frequency range, while fiber optic communication uses visible or near-infrared light. This means, well, we need a way to convert between these two frequency domains without losing any quantum information. Fortunately, scientists have developed devices called electro-optic modulators. These devices can imprint information carried by microwave photons onto light particles and vice versa. By integrating electro-optic modulators into quantum computing architectures, we can seamlessly bridge the gap between the microwave domain of qubits and the optical domain of fiber optic communication. This ability to convert between microwave and optical signals with high fidelity is crucial for building large-scale interconnected quantum computers. It allows us to leverage the best of both worlds, the stability of superconducting qubits and the speed and efficiency of fiber optic communication. Section 6. Scaling up, cost down, the impact of optical readout. The development of fully optical readout for superconducting qubits has profound implications for the future of quantum computing. Firstly, it paves the way for building much larger and more powerful quantum computers. By eliminating the heat generated by electrical signals, we can pack qubits closer together, increasing the computational capacity of quantum processors. Secondly, optical readout can significantly reduce the cost of building and operating quantum computers. The complex and expensive cryogenic wiring systems required for electrical readout can be simplified or even eliminated. This makes quantum computing technology more accessible to researchers and developers worldwide. The combination of increased qubit density and reduced costs will accelerate the development of practical quantum applications. We can expect to see significant breakthroughs in medicine, materials, science, artificial intelligence, and many other fields. Section 7. A quantum internet. Connecting the future with light. The ability to connect quantum computers using light opens up the possibility of creating a quantum internet. This network would allow quantum computers to communicate with each other over long distances, sharing quantum information and collaborating on complex computations. Imagine a global network of interconnected quantum computers. This network could tackle some of humanity's most pressing challenges, from developing new drugs and materials to modeling climate change and understanding the universe's fundamental laws. The possibilities are truly limitless. While the quantum internet is still in its early stages of development, significant progress is being made. Researchers around the world are working on building the necessary hardware and software to make this vision a reality. Section 8. The dawn of a new quantum era. The development of fully optical readout for superconducting qubits marks a turning point in the evolution of quantum computing. This breakthrough, coupled with the potential of fiber optic communication, paves the way for a future where quantum computers are no longer confined to research labs. We are on the cusp of a new quantum era, one where these powerful machines will transform industries, accelerate scientific discovery, and reshape our world in ways we can only begin to imagine. The journey ahead is full of challenges, but the potential rewards are too great to ignore. As we continue to push the boundaries of quantum technology, we can look forward to a future where quantum computers are as ubiquitous as smartphones are today, unlocking a world of possibilities for generations to come. Section 9. A final word: the journey ahead. The path to fully realizing the potential of quantum computing is still under construction. However, with each breakthrough like the one achieved by ISTA, we move closer to that goal. The ability to manipulate and communicate with qubits using light is a game changer. As we venture further into this exciting frontier, collaboration between researchers, engineers, and industry leaders will be crucial. Together, we can overcome the remaining hurdles and usher in a new era of technological advancement powered by the enigmatic laws of quantum mechanics. The future of computing is bright, and it's illuminated by the promise of light itself. Don't forget to like, share, comment, and subscribe to stay updated on the latest in quantum computing and technology.